Hi everyone, welcome to our video on a related rate problem involving a cube. Now I'm on this page because I wanted to refresh our memory of our four-step process. So far we've really only done the bottom two because we didn't need a picture, but in these next videos we're going to break down the whole thing because with geometry it usually requires us to draw a picture and figure out the variables on our own. Okay, so on this it says the edges of a cube increase at a rate of 2 centimeters per second. So here we see a rate. Well, they said the word rate, but also the centimeters per second is also a rate. So that means it's d something dt. And then it says how fast is the volume changing? So they want us to find a change in volume when the length of each edge is 50 centimeters. All right, so let's go ahead and let's draw. So the edges of a cube. So a cube. Let's try our best drawing here on the computer. Again, it's tough with the computer pen most of the time here. Okay, so there's a cube. So we've got the cube, and with a cube I know each edge is the same, and I'm going to use x for my variable. So it says the edges of the cube increase at a rate of 2 centimeters per second. Okay, so that's useful for us. We'll come back to it. I've got my picture. It's now asking how fast is the volume changing. Okay, so volume, I know how to find the volume of a cube. So the volume of a cube is base times width times height, but using my variable it'd be v equals x cubed. Okay, so that's the equation that's important to us in this problem. And then, so this was us drawing a picture. This was us getting the equation. So not too bad, huh? So even with geometry, at least the first two steps are usually pretty nice as long as we know how to deal with it. And then step 3, I'm going to go and get this derivative. So the change in the volume with respect to time would be 3x squared with, again, respect to time, dx dt. Okay, so we're doing the derivative. So step 3 was the derivative. And then step 4, I just want to plug things in. And I always just abbreviate it. We'll plug in stuff. Okay, so it's asking how fast is the volume changing. So dv dt is what I want to find. So we'll leave that like that. dv dt equals 3. And then let's figure out what we have. Okay, so how fast is the volume changing when the length of each edge is 50 centimeters? So they're telling us x is 50. And then they told us the rate. It says increases at a rate of 2 centimeters per second. Okay, so the increase in rates 2 centimeters per second, that's the edge. So our variable that relates to the edge is x. We need to make it into a derivative with respect to time. So all of that statement means dx dt is 2. And increasing means we want to keep it positive. So I want to keep it just as is, just 2, just like that. Okay, so anyway, so let's go back. So I just started writing my equation, dv dt. I just stopped at 3 because I needed x to be 50. And then it's going to get squared. And then dx dt is going to be 2. And then now it's looking real good, and we'll just wrap it up. dv dt is 3. 50 squared would be 2,500, and then times 2, and let's just multiply all that. We gives us dv dt equals. All right, so this looks like it'd be 15,000. Okay, so we have 5,000 times 3. Yeah, 15,000. And then the units for it. So this is dv dt. Again, I would want to make sure that I have the correct units. Now, one way to get the units is to think, hey, what's our unit for volume in this problem? Well, if my edges are in centimeters, the unit for volume would be centimeters cubed. And then per, what's the unit of time? Well, it looks like the time is in seconds. So it's centimeters cubed per second. But let's break it up one more time and state it in words. So this is the change in volume. So the change in volume is, all right, this is increasing, so we'll say, or this is positive, so we'll say increasing. The change in volume is increasing at